Hello, hello, hello. So, this is my first live stream, and today we are going to do like continue the lead neat code preparation, and we are solving the neat code 150 sheet, as you know. So, today again, let's get to the graphs. Let's wait for someone. There's no one is watching. इस लाइव स्ट्रीमिंग में इतना ही डिले रहता है क्या हमेशा? Like I am looking at comments in my phone. So today's question is rotting oranges, like this fruit, whatever it is. So lastly I have done that teaser and island question. It is similar to that. So let's first understand the problem statement. That is tough. Mm, mm, mm. So the problem said that you are given a 2D matrix grid. Okay. Each cell can have one of three possible values. Like it is kind of same that teaser and island question. Three possible values. 0 representing an empty cell. 1 representing a fresh fruit. Okay. And 2 representing a rotten fruit. Okay. Every minute, if a fresh fruit is horizontally or vertically adjacent to a rotten fruit, then the fresh fruit also became rotten. Okay, vertically and horizontally, not diagonally. Return the minimum number of minutes that must elapse until there are zero fresh fruit remaining. If this state is impossible within the grid, return -1. Okay, let's understand the example. I still don't understand that exactly what I need to do in this. Return the minimum number of minutes that must elapse until there are zero fresh fruit. Return the minimum number of minutes that must elapse until there are. Okay, so in 0 minute we will do this one. In second minute, do this one. In the okay, let's try it. So if in the last question I have done the similar thing kind of this. So in this the like the empty cell is 0 and 1 is representing fruit and 2 is representing rotten fruit. We will start with 1 and make it rotten. Like for this I still face issues in like logic building, yeah. In the last problem, that Treasure and Island, we have did the same, like kind of same. That we first find the gate. After founding the gate, we go to the like steps, getting distance to that gate and mark that as distance. That is this. Go right, left, up and down. Okay, this is okay. Like the problem said that we have to like start from an banana and then move vertically and horizontally and make them like clear whatever rotten it is. So for that, what is the best approach for this? I think so DFS will also work in it, but I think the BFS approach is far more better. The reason is in DFS we will like if this portion is blank in the grid, we will go deep down till we find an banana. If we didn't find, we need to like come back and start from here. DFS will not see the side columns even if they have fruits. So the BFS approach, I think it's a good approach that it have one banana on the right side or on the left side maybe. So let's start coding. I don't know like I will able to do this or not, but let's try. First start with row and column, that is length of grid, and column is length of grid 0. So after the like we also need to keep track of the rotten fruits. So for that we need a set, and if you know that in if you know graphs in BFS we need a q t q like now we need to find the fruit for I in range row, for j in range column, if grid of I and j equals to what are the fruits number, 1 is representing fruit. So if this is it, we need to add the location of that fruit. Add set dot add I and j. We need to add this in tuple cause set needs tuple as input, and also in qu dot append list I and j. So this is for the like there's a script for finding a fruit first. After finding, like let's comment it, Finding the root. I don't think there's any problem in it. I think it will work fine for this. And now we have QU. We need to handle that also. So for that, like we need to count the minutes also. So in every iteration, not in iteration, we need to find the minimum. So initially it will 0. Whenever it go horizontally or vertically, we need to calculate, like we can calculate in that helper function, I think so, that whenever it will go up and down. Yeah, maybe let's try. While we have QU, we need to iterate from it for I in range length of QU. QU, not QU, it's Q, sorry. And we have to like the row and the column location in the queue, so we need to pop that R and C, that is row and column. Q dot pop left, pop left. After popping, we need to make it visited. After popping, yeah, I think grid of R and C equals to minimum. The reason is that if we uh, if we bring the first fruit, like this is it, so our minimum initially is 0, and from where it will start, let's assume it will start from here. We assign it to minimum, like the 0 minute, so here our minimum is 0. In 0 minute we will like get the first fruit. Like I'm not able to think like how it I will track the every minute of this. So let's we have a add room, not add room, a rod fruit. Let's copy it. No one is watching, yaar. 92 subscribers and only 2 are watching. Well, it's my first live stream, so if you are watching, give it a like. So, rotten fruit, and we will need to go up horizontally and vertically. So, for that, R and C plus 1, mm, R plus 1 and C, R and C minus 1, R minus 1 and C. And after each iteration, do I need to increase the minute? Yeah, I think minimum plus equals to 1. The thing we didn't did is that in the end we will return the minute cause we need the minimum minute, and the problem we did that I didn't trust the minimum. Like how will I do that? Return the minimum number of minutes that must elapse until there are in few minutes. I think I am going to a tutorial. Return minimum, but I will go for the hints first, not the direct tutorial. Uh, as you notice that road fruit, we just call the function, but we didn't define that. So let's define it, which will take R and C. The base condition is if v goes out of bounds and our grid is initially 0, we need to do nothing. Oh, one more thing, one more thing, one more thing. Initially, we have one rotten fruit. Uh-huh. This is the problem I face in every single question, I think. Let's first call the function, then see if r is less than 0 or r is greater than equals to the row, or c is less than 0 or c is greater than equals to all, or another base case is if, yeah, we will map the grid, like grid of r and c is equals to the 0, which means an empty cell. We need to do nothing, return. Otherwise, we need to make the fruit rotten. So for that, we will take the path and make it rotten. So for rotten fruit, we need to make it 2 and do the same for all. Mm, mm, mm. Can I see any like hint from the last question? Cause it is similar to that. Even if they are similar, I find every single question a unique one. I don't know why this logic is not building. So after making the fruit rotten, we need to like track that we have marked that fruit as rotten. So for that, we need to also add that into the set dot add R and C and Q dot append R and C. It will not work because there are some reasons. If we found the like here, if we found the rotten fruit first, then are we able to make the other fruits rotten? Yeah, from here, if we'll go here, it will start from the corner, and we added that into the set and into the queue, and minimum we have calculated. Let's run it first. Time limit exceed. There's something that I'm missing and I'm not able to think in that way. I don't know why, but the only thing I can do is let's copy paste it as always. Gemini, Gemini replies like way more better than the chat GPT now. Understanding BST. This is my DSA chat in which I don't directly ask the solution always. I did this solution for the rotten fruit, but it's not working. So Teach me its solution with hint. Don't ask for the solution directly, because when you ask for the solution directly, your mind will like, I can see it. Your mind says like, I can see it. Then why I will try to like build muscle memory inside myself? So go for the hint, make your brain work a bit hard. That is the real optimization for the DSA solutions. You are very close. I know that you have the right BFS structure, yeah, but you are confusing this problem with the poles and gates. Exactly, exactly. I know that problem, but I can't think of this new problem. We wrote the distance into the grid in rotten oranges. The grid represents the state 0 empty, 1 fresh, 2 rotten. If you write the time example 3 into the grid, the code will think it's a rotten orange, since anything greater than 0 might look like an obstacle or target. Or just get confused. The three bugs in your code. The override bug. Grid R and C is equals to, you are overwriting the map. If you change a cell to 5, okay, because it's minute 5, the next neighbor won't know if that's a rotten orange or just a wall. Just mark it as 2. The condition bug. If grid of R and C equals to 0, your helper stops at 0. Uh, but it also needs to stop at 2 already rotten oranges. Yeah, there's one thing I have did. 0 is the blank space that we need to like iterate through, and where we don't need to iterate is the rotten oranges that we have already like rotated them. So for that 2, whatever that is, what I don't know exactly rotten means. Only proceed if grid R and C equals to 1. Yeah. The impossible bug. The problem asks you to return -1 if oranges never rode because they are trapped behind walls. Your code always return the time even if fresh oranges remains. Count the fresh oranges at the start. Count the fresh oranges at the start. What do you think? Do I need to like see the code now? The override bug. Grade R and C is equals to minimum. Just mark it as 2 rotten. Uh, I think so. Fix the count the fresh oranges at the start and subtract from that count as you wrote them. At the end, if fresh is greater than 0, return -1. I need to also track of the fresh fruits. Why do I need that? Return the minimum number of minutes that must elapse until there are 0 fresh fruits remaining. If this state is impossible within the grid, return -1. If this state is impossible within the grid, which state must elapse until there are 0 fresh fruit remaining? What if there are fresh fruit remaining? The problem asks you to return -1. I need to watch the solution now. Code DQ, yeah, I have did the fresh and time. I need to track of these things also. Why? Count fresh oranges and add rotten oranges to the queue. Fresh oranges. How many fresh oranges are there in the grid? For R in range columns, if there are fresh fresh, we will increase the count of fresh, and if they are rotten, we need to append this into the queue. Okay, direction helper. So for the direction, I have made that helper function, that is this part. BFS loop, we only continue if there are fresh oranges left to infect, while Q and fresh is greater than 0. The core solution. As you know, I'm also doing the Go language, so this is the code for the Go language. Not that much hard, but if you are going for any data structure, you will face the problem in it. Like in this, I will show you. For QU, you need to like write these kind of stuffs to make an queue, and the variables you need to make colon then equals to assign a variable, and also these kind of things in it. But let's get back to our problem. BFS loop, while we only continue if there are fresh oranges left to infect. Yeah, like we have stored the fresh oranges in the queue, so we will iterate through only if we have fresh oranges in the queue. For I in range, we have popped for direction and the distance in direction, column R plus dr, C plus dc. What is this? Okay, this is so what it did is that it will not create an helper function, it directly give the directions and make it possible in the while loop. So this is a bit confusing, but okay. Here it marked as rotten. I think the tutorial is way more good to like understand this problem. So for that I will go to rotten oranges problem. I see most of the solution of the NeetCode, like it is the original sheets owner, and he teaches very well, like in Python, if you want to learn.
Make a move with Hostinger Sale. Bring your idea to life with Hostinger Horizons AI. You just need to
Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve the problem rotting oranges. We're given an m by n grid where each cell could have 3 different values. It could have a 0, which represents empty. It could have a 1, which represents a fresh orange. Or it could be a 2, which represents a rotten orange. Every minute that passes, any fresh orange that is 4 directionally adjacent, meaning either up, down, left, or right. So if it's right next to a rotten orange, then that fresh orange will also become rotten. We want to return the minimum number of minutes that must elapse until no fresh orange exists. But it might be impossible, suppose if a fresh orange was actually not next to any other oranges at all, including any rotten oranges, then that fresh orange would never become rotten. So if it's not possible, a fresh orange number of minutes that must elapse until no fresh orange exists. But it might be impossible, suppose if a fresh orange was actually not next to any other oranges at all, including any rotten oranges.
Like, what does it mean that if, like, forget these oranges, this one, forget this one, these two oranges, forget in this grid, forget these two oranges, and we have this in the corner. So if this is remains, there's no like another oranges around here, so it will count as -1 because it is impossible to make it rotten. So this is what it means.
Oranges, then that fresh orange would never become rotten. So if it's not possible, then we can return -1, but if it is possible, we return the minimum number of minutes that it takes. So you can see in this example, which is actually a very simple one, because we are only given a single rotten orange, but we could be given multiple rotten oranges. But in this case, we see that this is the rotten orange, right?
Whoever watching this live streaming, please, can you
Right now we're at time
say hi
equals
in
0.
comment?
And let's say 1 unit of time passes, now we're at time equals 1. What happened? Well, the adjacent oranges to the rotten one also became rotten. So this is rotten now, and this is rotten now. Okay, now
As I told you that we need to go horizontally or vertically. So we can't go diagonally here. So if we are here, we can go the downside and the right side and the upside and the left side, not diagonally like here.
Now another unit of time passes as time equals 2. What happened? Well, all the other oranges which were adjacent to rotten oranges, like these two, also became rotten. Okay, now we're at time equals 3. What happened? Well, this orange, which is adjacent to a rotten orange, also became rotten. Now we're at time equals 4, and this last orange also became rotten because it's next to a rotten orange. So at time equals 4, 4 minutes later, all oranges are rotten. So we return 4. That's exactly what they expect in this example. Let's say this is the grid that we were given and these orange things are the oranges. And let's say these two initially were rotten. What kind of algorithm can we do to make sure that the adjacent oranges also become rotten and then track the time that it takes for, each layer to become rotten? Well, you could try a DFS, right? That's like the first graph algorithm that most people try. In this case, it's not really going to work. We run a DFS, let's say, on just one of the rotten oranges. Let's say we pick this one first. Okay, we run a DFS on the adjacent spots. Okay, here's an adjacent spot, so this becomes rotten. This becomes rotten. That's time equals 2. Then this becomes rotten at time equals 3. Then these two become rotten at time equals 4. And then lastly, this one. But that doesn't really work because it took us 5 units of time to make these rotten. But that's not actually what's going to happen, right? These two initial rotten oranges are simultaneously going to be making the adjacent oranges rotten, right? Like after 1 unit of time, this orange is going to become rotten from this one, and this one is going to become rotten from this one. After another unit of time, this is going to become rotten from this one, and this is going to become rotten from this one, and this is going to become rotten from this one as well. After 2 units of time. After 3 units of time, this last one is going to become rotten either from the one above it or from the one to the right of it. So in 3 units of time, all of the oranges became rotten. But we didn't use DFS. If you were watching carefully, you might have noticed that the main algorithm we were actually using is BFS, breadth first search, right? Which is also a standard algorithm. And the reason it's helpful for us is because we don't have to finish running DFS on a single rotten orange. We can run the BFS algorithm simultaneously on multiple sources at the same time. So basically what we're doing is running multi-source BFS. And usually BFS is implemented with a queue data structure. So basically what we're going to be doing is initializing our queue with the initial rotten oranges. We're going to pop through every initial rotten orange, and then we're going to call that 1 unit of time. And then to our queue, we're going to add the next rotten oranges. So these two would not be in our queue anymore, but this one over here and this one over here would then be added to our queue, and then we're going to pop through those ones as well, and then call it our second unit of time, and then keep going like that. But how do we know when we're actually finished? Well, once our queue is empty, then of course we can stop. But it's not guaranteed that we will actually have made every single orange rotten. Suppose there was an orange all the way over here that's a fresh orange. It's not rotten yet. Of course, we know that these oranges are going to become rotten, but this is not going to become rotten. So basically, after our queue is completely popped, what we're going to notice is there is a fresh orange remaining. And the way we're going to know about that is because we should keep track of how many fresh oranges there are initially, right? In our case, I think there's about 7 fresh oranges, right? And then by the time our BFS algorithm is done, we're down to 1 fresh orange. Because we still have a positive number of fresh oranges, that means we were not able to make every orange rotten, and therefore we're going to have to return -1 as our result. But if we were able to do that, right? Let's say this orange didn't exist. We, make all these oranges rotten. Then we keep track of how much time did it take us to make all of the oranges rotten. It was 3 units of time, I think. So then we're going to return 3. So that's the overall algorithm. As you can kind of tell from the BFS, it's multi-sourced, but we're still only going to be visiting each orange, each cell in our grid at most once. So we can say that the time complexity is going to be n times m, where these are the dimensions of the grid. And I think in the worst case that the memory complexity is...
When you have like two input variables, like in this problem, in graph problem, we have two input variables, the rows and columns. Not in graph, like mainly in every DSA question, if there are two input variables, like in a string there are two strings, so the time complexity will go to the initially it will go n into m, that is n is the number of rows and m is the number of columns here, and sometimes it might go n plus m, and this will apply in the string also, because if there are two input variables as a string, we will count the length of the string 1 and the string 2. So mainly that will be going to be the time complexity in the two input variables.
also going to be the same because we're going to be using a queue and all that. So that's enough for us to get into the code. So let's do that now. Okay, so now let's code it up. So the first thing we're going to do is initialize our deck. It's going to be empty initially. We're going to also have two more variables. One is going to be the time to keep track of how much time has passed. And another is going to be called fresh to keep track of how many fresh oranges we have at any given point in time. Initially, let's just set these both to 0, but let's actually iterate over the entire grid. And actually, before we do that, it would be good to get the dimensions of the grid, so the number of rows and the number of columns. So now let's iterate over the entire grid just to do some pre-work. The pre-work is going to be doing two things at the same time. So we can just write some nested loops to iterate over the grid. One we're going to be doing is counting the number of fresh oranges, right? So if any cell in the grid is equal to 1, remember that 1s represent fresh oranges. So if this is equal to 1, we can just increment the number of fresh oranges. The second thing we also want to be doing is to identify all of the rotting oranges, because remember, we need to add them to our queue so that we can actually run the BFS in the first place, right? The multi-source BFS. So if any of these grid cells are equal to 2, that means it's a rotting orange, and that means we can go ahead and append it to our queue. And by append, we're going to be appending the coordinates of that rotting orange. So next, what we're going to be doing is running our while loop while our queue is non-empty, and we can say that if fresh is also greater than 0, right? Basically, if either of these, if our queue becomes empty or if fresh equals 0, then the loop is going to stop. If neither of those are true, then we're going to continue the loop. So now we have a certain number of rotten oranges in our queue, and we want to actually pop every single one of them. So basically, we're going to create another loop while, let's say we have 3 oranges in our queue, then we're going to iterate through the loop 3 times. We're going to pop those 3 oranges, but at the same time, we're actually going to be adding the adjacent oranges to that queue as well, marking them as rotten. So that's why we're creating the for loop rather than saying while the queue is non-empty, because this will just take a snapshot. So for example, if the length of our queue is equal to 3, this loop will execute 3 times, even though inside of the loop, we're going to be adding to the queue, updating its length. But this, the range function isn't going to execute each time after that. We want to, of course, pop from the queue. And when we pop, we're popping the coordinates of the rotten orange. At this point, we want to go through all of the 4 adjacent spots for this orange. So what we're going to say is DRDC, the difference in row and difference in a column, in directions. And we're actually going to create a variable for this outside of our loop. And it's basically the 4 directions that we could move in. So it's going to be pairs, let's say 0, 1, and 0, -1, and 1, 0, and -1, 0. So these are the 4 directions we could move in. So that's what DRDC is going to represent. So let's actually calculate what the row would be. So initially we're starting at RC, and then the adjacent spot that we're looking at is going to be DR plus R. and DC plus C. So this is one of the 4 adjacent spots, row column. And what we want to do with this position is make sure that it's in bounds and that it's a non-rotten orange. So meaning that it's a fresh orange. Let's actually change this comment to that. And it's a fresh orange. And then we want to make it rotten. So to save a bit of time, I'm actually just going to copy and paste this. So what we're doing here is checking that the row, basically if the row is out of bounds, if it's less than 0, or if it's too big, or if the column is out of bounds, or it's too big.
I can guarantee once you start trading with AI, you'll never want to go back to doing it manually. The results?
Or the grid cell is actually not a fresh orange. If any of these are true, we're going to continue to the next iteration of the loop, because that means this is either out of bounds or it's not a fresh orange. But if it is a fresh orange and it's in bounds, then we want to make it into a rotten orange. So we can do that very easily like this. And we also want to add that position to our queue, so that row column pair, so that over the next iteration of the while loop that we can include that, right? Even though we're appending to the queue, this portion of the for loop isn't going to change, right? That length was a snapshot. We're not going to continuously update that. And last but not least, make sure to decrement the number of fresh oranges, because that's one of the indicators of if we can stop the algorithm or not. And remember, this loop was going through all of the rotten oranges, and then the adjacent fresh oranges were being set to rotten as well. So that actually happened in 1 unit of time. So after that loop is done executing, we can increment our time by 1. After this loop is finished, then it's time to return our result. But how do we know if we can return the time or if we have to return -1? Well, we can return the time if fresh is equal to 0. That means we made every single orange rotten. But else, if it's not, then we have to return -1. That means there's some oranges that we just can't make rotten. Okay, so that's the whole code. Now, lastly, let's just run it to make sure that it works. And actually, I just noticed I made a couple of little mistakes. So over here on this line, I forgot one of the OR statements. So let's add that as well. And actually, here we have queue.pop. But remember, we're actually adding to the queue. When we append, we're adding to the right side of the queue. So when we pop from the queue, we want to make sure we're popping from the left, because we want to pop the more recently added oranges, right? That's why we're taking this length. If the length was 3, we would want to pop the 3 oranges from.
So this was the solution. Like it is not that hard, but I don't know why I was not able to do it. I will do it in the evening, cause I don't do any DSA question in like instantly after watching that tutorial. So for now, bye. There's no too much views I can get on my live streaming, but if you are watching, this is my first live streaming. Like it and give it a comment.